So, my name is Jordan Hammond. I'm with Clay Chesser, and we are going to be discussing, the use of optical tweezers to determine the viscosity of certain fluids. So, let's get started with our introduction. So, what are optical tweezers? Well, in essence, optical tweezers are kind of, as the name suggests, they're essentially tweezers made out of light. Through concentration of high energy light to a certain point, we can actually create really small forces on tiny objects. Obviously, the forces are really small, so we can only observe them on a microscopic scale. But it's through the concentration of high beams onto a certain target. In order to create any sort of observable force, you have to use, high energy beams. You can't just do this with a simple LED or anything like that. And the trapping force that's created with an optical tweezer acts kind of like a spring, where as the target is displaced from the center of the trap, it starts to feel an increase in magnitude of the trapping force, on the order of magnitude of some, spring constant that's kind of unique to the trap. And because of this, if the trapping force of the tweezers is known, then we can actually use tweezers to test other forces acting on our target. So, from a certain displacement, we know the magnitude of the trapping force that's acting on it. So we can actually, match the trapping force that the target is feeling with respect to its displacement to some other force that's acting on it. And we can also manipulate certain targets through the use of optical tweezers. Optical tweezers have useful applications in a lot of different fields because of their versatility, because it's really just a tool. So tools can be used for many different things, right? One application is biology and medicine. We can manipulate certain cells. So if we need to do some sort of procedure on someone, and we want to do it in a non-invasive manner, we can actually use optical tweezers to manipulate, certain cells and things like that on a microscopic scale within someone's body or something like that. We can also study the microscopic or molecular forces that are acting within certain proteins. For example, when DNA is being transcribed, we can actually measure the force with which a strand of DNA is actually pulling as it's being transcribed. If we just attach one end of the strand of DNA to a certain microsphere, a certain microscopic bead that's being trapped by optical tweezers, we can look for the point at which the bead is in equilibrium, and then we know that the force with which the DNA strand is pulling on the bead is going to be equal to the force with which the optical tweezers are pulling on the bead. And again, we can calculate that force using some sort of spring constant and the displacement of the bead. There are also applications in material science. So if we need to manipulate or test certain materials on a nano scale, we can see how materials act under certain conditions when they're being tested on a really small scale like that. If we need to fabricate nanotechnologies, right? If we need to move certain components around and we can't do it with normal tools because it could damage the components, then we can actually use optical tweezers to move those components around without actually having to physically touch them and risk damaging them. In quantum computing, there's even applications because we can manipulate qubits, at a distance, or, we can change their states remotely through optical tweezers. And there's also applications in microscopy. So, through certain imaging, from the information that we're able to process through optical tweezers and through the effect that certain objects have within the apparatus, we can actually create, high fidelity images and extract a lot of information about the physical properties of certain things that we wouldn't be able to do normally. And getting into the basic theory of how optical tweezers operate. So let's focus on the actual optical trap that we're creating here. So again, the optical trap is created by focusing, concentrating a high energy laser beam onto a specific point, onto a specific target, typically, a really small particle, a really small bead or something like that. And so what's going on here is, well, first of all, we have to use high energy waves, or high energy light, I'm sorry, because, as that light is passed through our target, as it's refracted through our target, we can observe a change in the beam's, direction, which correlates to a change in its momentum. Well, of course, if the photons are changing in momentum as they pass through this target, that means that they need to be transferring their momentum to the target itself. And so that's kind of how this force is created. It's because of that change in momentum of the actual photons passing through the target. And so what we notice is that an intensity gradient is actually created at the focal point of this beam. And so there's an actual change in intensity with respect to position as we move around in the focal point of this beam. And microscopic particles tend to experience optical force towards the direction of increasing intensity, which, of course, if the point of highest intensity is the focal point of this beam, well, then naturally, any particles that are trapped in this optical trap are going to be moving towards the focal point because they want to move into the direction of higher intensity. And naturally, because of this, as we displace a certain target within the trap, if we move it away from this point of highest intensity, it's going to want to naturally move back into that direction, into that point of higher intensity. And so we can see that it actually wants to displace back. It feels a force back into the center of that trap, again, kind of like a spring. And because these particles want to stay in the center of the trap, we can actually naturally, if we want to move the particle itself, all we have to do is move the location of the center of the trap. So we can actually manipulate certain particles by trapping them within these optical tweezers, then actually moving the location of the center of the trap itself. And one thing to note is typically when we use optical tweezers, the target that we're trying to trap is kept in a fluid, a kind of a liquid medium, typically. And because of this, the target that we're trying to trap will experience this thing called Brownian motion, which is just random motion as a result of the thermal energy within the medium that the target is resting in. And this is very prevalent in fluids and liquid media, sorry. And this is kind of something that we'll get into more in a second. But then obviously, if we're trying to study the motion of certain microscopic particles that are being trapped with optical tweezers, we're going to need some sort of method of detection. And so for the sake of this experiment, we're using a Thorlabs optical tweezers apparatus. And so the method with which that apparatus actually measures or detects the displacement of the optical target is through a backfocal plane detection module, which we then hook up, to our computers and stuff like that. And we can actually use, analysis software to actually model the displacement of the target through that. And in order to actually measure the viscosity, we're going to need some sort of, the whole point of this experiment is to actually figure out what the viscosity of the medium is that this, microsphere is resting in. And so we need some sort of method for doing that, some sort of mathematical analysis probably. And so, the particle that we're trapping here actually ends up undergoing Brownian motion, of course, because it's going to be kept in, different liquid media. And that Brownian motion is then going to be detected by the backfocal plane detection module in our optical tweezers. And so because the target is naturally going to undergo this random motion, this motion is going to actually be resisted by the viscosity of whatever material it's in, or whatever liquid medium it's in. So it turns out the motion of the particle itself is inversely proportional to the viscosity of the medium that it's in, which is actually very useful because the particle is naturally going to want to be moving around in this set of optical tweezers, so we can actually study the change in this motion to figure out the viscosity of the material it's in. And the way we do that is through the Einstein-Stokes relation, which describes Brownian motion and in turn reveals the viscosity of a fluid. You may ask, what is the Einstein-Stokes relation? Well, it's this equation right here, that relates this thing called the diffusion coefficient, which we calculate using the Boltzmann constant, the absolute temperature of whatever fluid we're studying in Kelvin, a couple constants, the viscosity of the fluid, and the radius of this trapped particle or this microsphere, which are all things that we actually end up being able to know or calculate. We'll actually get more into the details of this calculation in later sections, but this is kind of the basis of our analysis as we're trying to figure out the viscosity of these fluids. And now we can move on to the actual experimental setup.
So we're looking at the experimental setup. We got a list of materials here. So obviously, first up, we have the optical tweezers apparatus, along with the other instrumentation that can be seen on the diagram to the right, most notably the backfocal plane detection module and the laser diode and controller and camera and such and such. Either way, next we have the microspheres of known radius, which would be 55 microns. And then those have to go into our sample fluids, which would be water and glycerol. We also have some analysis software, obviously first up being noticed, the focal plane detection module, along with some outside Python code that I wrote along with Jordan to use to analyze the Brownian motion as talked about before, and the other values that we'll need to be solving and proving the equation from Einstein and Stokes. So the procedure, first up, we need to calibrate the optical tweezers to determine the force on trapped microspheres. So we can't have too strong of a force or too little of a force, or either it won't move or it will just slide out of it, respectively. And then after that, we just place the sample fluids onto the sample slides and place the microspheres into the sample fluid slides. Next, we would then trap the microsphere using the force that we determined in the setup in each fluid individually, and then of course then readjusting and ensuring that the trapping force is of a proper magnitude so that the microsphere stays within inside of the trap. Next up, we do some analysis, mainly of the Brownian motion. There's a 2D plot of it that I have on the next slide with the mean squared displacement values and a plot of that as well over time. And we'll look at that here in a second. But before we get there, we need to record all of that motion using the back focal plate and use some image analysis software that I have in Python and some other sources to track this microsphere displacement. So here's our results and analysis. As can be seen on the left, we have the plot of the Brownian motion for a microsphere in water. The water's temperature is 298.15 Kelvin. The diffusion coefficient that we get from the Einstein and Stokes equation from before is that 4.49 E negative 15. And then obviously the real viscosity that is from a scholarly source, 8.9 E to negative 4 pascals seconds, I believe is what that unit is. And then the calculated one that we got from this Brownian motion and the mean squared displacement over time graphs above was that 8.83901 E negative 4 pascals. So obviously very close in relativity to each other. So very good for our data and analysis to be able to prove this relationship from the equation. And then this can also be seen in the next slide with the Brownian motion of the microsphere and glycerol, as well as the mean squared displacement over time graph on the right. And we calculated that viscosity to be 145,374 E, so with zeros. So, and then the real viscosity, of course, being that 1.414. So again, very close, proving that, you know, our analysis and our data was good, and that we are able to prove with mathematical backing and evidence from the collected data that this relationship is true. And you'll notice that the temperature did change. We had to bump the temperature of this liquid down 5 degrees to get to a known viscosity that was accurate. instead of the 25 degrees Celsius or 298.15 Kelvin. This way we could ensure accurate data and accurate measurements. And then the diffusion coefficient that we received from this one is 2.73 e to the negative 18th, which can be found from the graph above and the mean squared displacement over time. And then next, we have our graphs of these slopes. The main focus of this is that the slope is equal to 1 over 6 pi r. So obviously the inverse of the slope is 6 pi r. So 6 pi r with r being 55 microns, you can see that we get pretty close estimates of what it's supposed to be from both of these graphs, telling us again that our data is correct or is at least valid and can be used to prove the relationship from the Einstein-Stokes relationship. And then moving on to the conclusion. Potential sources of error, miscalculated constants. So the temperatures, if anything changed in between the time of measurement to the time of use, you could end up with something a little more viscous or a little less viscous than wanted. Interference with displacement measurements. So any bumping of the table, anybody walking, and sometimes even walking outside the room, anything like that, it can have an effect on it, even if we don't see it. So it happens. Impurities in the fluids, so something like the glycerol not being quite 100% equally dispersed. So if you have little pockets of it, or even little pockets of the water molecules that are densely packed in one area and not packed in a different area, this can create, different pooling and different issues for your Brownian motion models and your mean squared displacement overall. The experiment suggests that the optical tweezers can be used to accurately predict the viscosity of a given fluid, given that you calculate your your diffusion coefficient and use that to create the graphs for the slopes that tell you that your 6 pi r is close to the actual value of a calculated 6 pi r from the relationship stated beforehand. Other than this kind of experiment, optical tweezers are valuable for research in medicine, as stated before, and other fluid dynamic and anything really to do with microscopic particles, anything on the microscopic scale that you can use a laser to trap with. So anyways, that is the end of the video.